All right, continuing on, in this section we're going to look at the complement and addition rules that get used in probability calculations. So according to the information shown to the right, what is the probability that it will not rain on Friday? So we have to kind of figure this out a little bit. They're saying in this city that it's going to rain on Friday night, maybe, and they're showing us a raindrop right there and saying there's a 30% chance of it. So that's our probability that it will rain that night is 30%. So what's the probability that it won't rain? So they don't list that, but I think that it's fairly intuitive to say there's a 100% total possibility. So you can subtract that 30% away and say that there's a 70% chance of it not raining if there's a 30% chance that it will. If you did that in probability form, the 100% would be a 1, the 30% would be 0.30, and when you subtract you get 0.70. And doing it in that decimal form is the way that we have our rule written out that goes with that. I think this is intuitive to do it in the percentage way, but this is just the same thing written in decimal form. So the complement of an event is the event that consists of all the outcomes that are not in that event. So if the event, throw T in there, if the event E, the complement of the event E is all the things that are not in E. And the way we write that is by writing the word not followed by the event. So here's an example, probability of not E. And if you were to think about that in terms of a Venn diagram, E is inside of this circle and inside of the box. Not E is going outside of the circle but still staying inside of the box. So the box represents our entire sample space, everything that could possibly happen when we do the experiment. And when we say that it's not E, it's just subtract away everything from that center. So, but subtract from what? The total. And in probability, the total is 1. So the probability of an event will not happen is 1 minus the probability that it will happen. And so that's known as the complement rule. It's kind of intuitive in the sense that I think without knowing much about probability, if somebody told you there's a 30% chance it's gonna rain, what's the chance it won't? I think most people would subtract that from 100 and say 70%. This is just formalizing that with some probability notation. All right, so let's think about that. What is the probability that the next person you meet will not be born in July? So what we would want to do there is say the probability that they won't be born in July is 1 minus the probability that they would be born in July. And they want us to do this from the theoretical point of view. And even though all the months are not equal in their number of days, when they ask you this type of question in my math lab, they just want you to think of it as 12 months. I think this is a little distorted because July is a longer month than February, right? And then we're not even positive that people are equally likely to be born in all the months. But what they want us to do here is take 1 minus the probability of July and to think of July as 1 month out of 12. And then you could say that's 12 out of 12 minus 1 out of 12, which is 11 out of 12. But we usually go to a decimal anyways. So you could go to a decimal without doing the common denominator work, just 1 minus 1 over 12. If you wanted to do it as 11 twelfths, it would be the same. But you can save yourself the fraction work. If you know they're going to a decimal, as soon as you get it written out some way as a fraction, you could go to the calculator and get 0.9167. So there's about a 91.67% that the next person you kind of randomly come across would not have been born in July, assuming that people are equally likely to be born in all given months. I think that's probably a little flawed. That's why empirical probability would probably be better here. Go look at birth records and see what percentage of people are born in July and subtract that away from 100%, or subtract it from 1 if you're doing this as a decimal. Probably more accurate than making the assumption that every month is equally likely. But that is what they want you to do in my math lab, so I'm going to show it to you that way. All right, another definition that'll lead to another rule for us. Disjoint events. Two events are disjoint or mutually exclusive if they have no outcomes in common. So for such events, or questions can be answered as follows. Let me draw you a picture first before I give you the rule. If we drew a Venn diagram, disjoint events are separate. There's no overlap. So you have an event A over here and you have an event B over here, but there's no outcomes in common, so there's no overlap like we talked about with our Venn diagrams earlier. And when that's the case, it turns out that you can just do the probability of one of them and add the probability of another one. And so we could do that for our quick service restaurants problem that we did earlier. If they ask us for a probability about things from this list that are not overlapping, and I think if you read these carefully, you'll realize none of them are overlapping. There's no outcomes in common between any of these different pieces. That's why they're separate wedges of the pie. Okay, so let's go ahead and try out this rule on this pie chart question. So use the pie chart to determine the probability that a randomly selected survey respondent visits quick service restaurants at least 3 times a week. If that's not already written on your handout, please fill it in. That was an initial mistake. But at least 3 times a week means 3 or more. So that would be all these groups. We already kind of did something like this before we even had the rule. It was kind of intuitive. We just added those together. This rule officially says that's okay to do. If there is no outcomes in common, then you can just add the individual probabilities. So that probability becomes 0.144 plus 0.055 plus 0.067. Now I switched those to decimals in my head as I wrote them down because we tend to do decimals for probability. You don't have to do that first. You could just add up the percentages and then convert to a decimal at the end, but eventually you'd want to convert it. And I've done a lot of these, so I feel pretty comfortable just doing those conversions quickly in my head as I write it down. 0.144 plus 0.055. That's often a tricky one for people. They just want to move the decimal to the front and say 0.55, but that'd be 55%. That conversion is always moving 2 places. And then plus 0.067. So it looks like 0.266. So if I was going to interpret that, I would say there's a 26.6% chance that a randomly selected survey respondent would visit quick service restaurants at least 3 times a week. All right, let's look at our spinner example again. Use the graph to determine the probability that the pointer will land on an even number. So we could shade the even numbers. We've got 4 and we've got 2. So that's the part we want. Again, you have to be a little careful there. You can't just say that's 2 out of 4 possibilities because they're not the same size. So we'd want to chop it up like we did before, drawing in the extra lines to make all of these the same size. And when you do that, it looks like the size is 1, 2, 3, 4, 5, 6, 7, 8. So each one is an 1/8. And then how many do we have shaded? Well, for it to land on the number 1, well, first of all, we could say this. That's the probability of an even number. For this particular spinner in the possibilities is the probability of 2 or 4. But then using our rule up here, because those don't overlap each other, they don't have outcome in common, we could do them separately, the probability of 2 plus the probability of 4. And then we could look at the shading and say, what is the probability of 2? That's 1/8 of the area of that spinner, plus 4, which is 2/8 of that area. So altogether, the probability would be 3/8. And then we generally would go to a decimal on that. So if you do 3 divided by 8, you get 0.375. So there'd be about a 37.5% chance that that spinner would land on an even number, meaning either 2 or 4. But we did use this rule up here to do it. They're disjoint because they don't have any outcomes in common. They're separate parts of the spinner. And then we just added the 2 probabilities separately, though it is important on the spinner type situations to make sure that when you think about the probability, you're not just thinking about possibilities, but equally likely possibilities. And we get that from cutting up the spinner into equal size segments, 1/8 of which were 2, 2/8 of which would be the 4 for 3/8 altogether, or 37.5%. All right, so we just saw that if things are disjoint, we can add the two probabilities separately, but you can get into trouble if you tried to apply that rule when things are overlapping each other, when they do have outcomes in common. If you were to do that, if you were to take all the things from A and add those up, and then you were to go back and add all the things from B, you would get everything you needed, but you would double count this overlap wedge. So we want to be careful that when we do the counting on the green, we kind of stop that on just the new stuff. That we just take this little wedge out right here and we say, count all the stuff in A, yes, but when you count B, just count the new stuff. So the general addition rule states that if you're trying to find the probability that one event or another event will occur, then if you were going to think of that as a formula, you would want to think about the probability of A, but then when you do the next one, you'd want the probability of B, but you'd want to subtract out the probability of the overlapping part, which we call an AND. Not that you don't want the overlap, but if you count A and B, you count that twice. So this is the way they usually write the rule: count all of A, count all of B, and then subtract the overlap. I like to think of it with like parentheses around this part, or brackets. Count all of A, but when you count B, don't count the overlap. Don't count it, right? Subtract, because you already have that part. Only count the part of B that wasn't overlap. So in words, when two events are not disjoint, so they have something in common, you have to worry about this double counting problem. So we should determine the numerator of that probability by counting all of the outcomes in the first event, every one of the things in A, but then only adding in outcomes from the second one that have not already been counted. So only the new stuff when you move on to the second event. So that's real important. Keep in mind that you don't double count. The rule could say double count and subtract the extra. I think you'll do better in probability if you avoid the double counting in the first place, and the words version tells us that. All of the first one, but only the new stuff from the second one, only the stuff that has not already been counted. When we're asked about an AND, all this stuff we've been talking about so far where we're adding things together is for OR questions. What if they ask you an AND? Well, the first thing you need to know is, how do you visualize an AND? If somebody says, I want the probability of A and B, what are they talking about? And the important thing to realize is that they're just talking about that overlapping part. So the probability of A and B, we might write that also with that symbol, is the probability of the overlapping part. So let's go ahead and try and think about some examples of using AND and OR and thinking about this, and also thinking about maybe if they're disjoint, how that would play into. So we'll start off with some simple things and then go to something a little bit more complicated and see how it works there. So consider the roll of a balanced die. Find the probability that the number you get is odd and it's less than 5. So visualizing, I think, on these things is helpful. So I would write out the sample space. If you roll a die, you could get a 1, a 2, a 3, a 4, a 5, or a 6. So just kind of visualizing everything that's possible. When you do that, you've kind of sorted out what your denominator is. But now for the numerator, when it's an AND, you only want to count the overlap. So let's do the odd numbers, 1, 3, and 5. And then let's do the ones that are less than 5. The words less than are not inclusive, so that would just be 4 and down. But it's an AND, so we want the overlap. So we want the things that are overlap to be encircled in kind of this maroon and also be encircled in the purple. So the 5 is only in maroon, the 4 is only in purple, but the 3 is in maroon and in the purple, so that's part of the overlap, and the 1 is in maroon and the purple, so that's part of the overlap. So out of the 6 numbers, how many of them met both the description of being odd and being less than 5? Just the 1 and the 3. And so that would be 2 out of 6, or 1/3, or approximately 0.3333. Let's try that again, sticking with the idea of the die. So consider that you roll this balanced six-sided die. What's the probability of getting an even number or more than 3? So first of all, let's list the sample space. 1, 2, 3, 4, 5, 6. Those are the things that can happen when you roll the die. And then let's mark off the events. So even numbers, 2, 4, 6. And then the other one is more than 3. So more than 3 does not include the 3, so that would be 4, 5, 6. The way an OR is different from an AND is instead of just counting the overlap with the OR, you count all of the first one, and then from the next version, just go to stuff that hasn't been counted yet. So let's think about, first of all, our sample space. There were 6 numbers, so the denominator is 6. And let's count all of the ones that were even, which are the ones I circled in the kind of purple. 1, 2, 3. And then add on anything that's in the green circle, but only if it has not already been counted. We've already counted the 4 and the 5, so the only new thing is that one number right there, the 5. So when you do an OR, count all of the first one, 1, 2, 3 things circled in purple, and then say, is there anything new in the green I don't have yet? Yeah, there's one number there that's new that I don't have yet. And so we get 4, 6, which is 2/3, which is 0.6667, or 66.67%. All right, let's look at one last of these. Consider rolling that balanced die. What's the probability that what you get is not a 4? So again, what's our sample space? 1, 2, 3, 4, 5, 6. And I just want to point out the use of the complement rule here. When they say what's the probability that it's not a 4, we could just think about what that is, what number it could be. But according to the complement rule, we could take the total of probability, which is 1, subtract out the probability that it is a 4, and that should give us the answer 2. And if we do that, we do 1 minus the probability of a 4, and a 4 is just 1 out of the 6 numbers. If you do that with a common denominator, you'll come up with 5, 6. When you go to the decimal, you have a choice. If you did the common denominator work, you might as well enter in the 5, 6 to get the answer. But if you just wrote it out this way, that would be good enough too. 1 minus 1, 6, you get the same decimal. So 0.8333. So always good to remember this idea that when somebody says what's the probability that you don't get a certain thing, you could think about what does it mean to not get a 4. It could be a 1, a 2, a 3, a 5, or a 6. That's 5 out of the 6 numbers. But you don't really have to think about what the other numbers are. Just subtract out the probability of it getting a 4. But subtract from what? From the total. And then when you're doing probability, the total is 1. All right, we're going to finish this section up with one more example that involves a two-way table. And as we work through this one, we're going to get a little bit of a review of some of the things we saw in the previous pages. A 2011 survey asked 1,120 Americans if they believed that laws covering the sale of firearms should be made more strict, less strict, or kept as they are now. The responses are summarized below, together with the region of the country that the respondent is from, and this data is based on a Gallup poll. So if a person from this group is randomly selected, determine the probability that, and let's look at all these different parts. So part A, the person is from the East and they favor less strict gun laws. So the first thing I want to do is write out some notation for this. So we're doing a probability, so I'll put P of, and the person is from the East is event R1, and then we have an and, so I'll write that out there. And then we want that they favor less strict gun laws. So less strict is right here, and that is event A2. So we're doing an and we said earlier on previous pages that and means overlap. So what I want to do is go ahead and use red for part A, and I'm going to circle R1 and A2 so that we can see the overlap. So R1 is here, and then A2 is here, and means overlap, so when we do our probability calculation, we want to just count the parts that are in the overlap of those two red circles. So first of all, when we select, we're selecting someone from this group. So there are 1,120 different people that could be chosen, the grand total from our table. And then because it's and, we just want the overlap, and we can see hopefully nice and clearly with the two circled events that the overlap has 151 things in it. So then the probability of R1 and A2 is 151 over 1120. And again, we usually want to go to decimals on these, so I'll bring in the calculator and do 151 divided by 1120 and round that to 4 decimal places, which is what I like to do, so 0.1348. All right, so with the and, we're thinking overlap. Let's look at the next one. The person favors more strict gun laws, or they are from the South. So same idea, let's start off with the translation. So they're asking us for a probability that the person favors more strict gun laws. So more strict gun laws is A1. And then this time it says or, so I'll write that in there. They are from the South. So the South is right there, that's region 3. All right, so let's go ahead and think about that one. I'll do this one in teal. All right, so with an or, it's all of the first and whatever is new from the second. In the Venn diagram sort of way of thinking about this, if we had the two events, we would count everything from the first one and then whatever was new from the second one. So I basically want to mark up my Venn diagram just like I did, or mark up my two-way table just like I did the Venn diagram. So I want to shade all the stuff from A1. So that would be this square, this one, and this one. I don't want to shade the total because that would just be recounting all of these things. And then I want to shade the stuff in R3, but only stuff that's new. So I don't need to shade 79 again, even though it's R3, it's already shaded. But I do need to add shading for 101 and 28 because those are in R3 and I hadn't counted them yet. So how many total things have I got shaded? Looks like 1, 2, 3, 4, 5, 6 squares all together. And so what I want is to count all 6 of those up for my numerator. The denominator will be the grand total of the table because we're picking out of the whole table. So there's 1120 in the denominator. And I could just add up all these numbers, 231 plus 56 plus 79 plus 141 plus 101 plus 28. But it will be a little faster if I add all 4 of these at once by taking advantage of the total 507. I would not want to then add the other total 208 because if I do that, I'll count this square twice. So I usually just use one total and then I think about what has that gotten for me. That's these 4 squares. So I just need these 2 added on. So plus another 101 plus 28. So all of A1 plus the 2 squares in R3 that had not been counted yet. And then you could add all that together to get a fraction, but really what we want is a decimal. So I just like to go to the calculator from here, put that in parentheses to make sure it gets calculated correctly. So open parentheses, 507 plus 101 plus 28, close that up, that's the end of our numerator, and then divide it by that grand total of 1120. Round it to 4 decimal places, 0.567. And then it's an 8 followed by a 5, so I'll round that 8 up to a 9, and that would be the answer for the OR question. All right, let's move on to the next one. The person is not from the West. So first the notation, we want the probability of something. We want the probability that the person is not from the West. The West is region 4 up here, so R4. So we're looking for the probability of not R4. So there's a couple things we could do. We could do 1 minus the probability of R4, but I'm going to think back to like a while back when we were doing the marble jar, and I'm just going to do this. I'm going to say, all right, there's 1,120 people that are represented in this table, and I want all of those people except for the ones that are R4. So how many people are R4? Well, there's R4 in the table, and the total number of people that are in that group is 320. So I'm going to subtract those people out because it says I do not want the R4. So I want everyone from the chart except for the ones that are in R4. And then I can go ahead and go to the calculator. I'm not going to write the parentheses here, but you always need them when there's subtraction or addition. And then we can round to 4 decimal places. So 714, and it's a 2, but followed by an 8, so we'd round that up to a 3. All right, on to part D. What's the probability the person is from the Midwest or from the South? Okay, so the probability that they're from the Midwest, that's region 2. And it said or. they're from the south, and the south is region R3. So that's what I want. And if you look at this on the chart, I'll go ahead and circle these in green. So if we look on the chart for that, we have R2 is the Midwest. So that's here. And then we have R3 for the South, which is right here. And as I circle those, what you should notice is they don't overlap. So when things don't overlap and you're doing an OR, you can just add the total from here to the total from there. The risk of doing that addition normally is that you would double count things. But if there's no overlap, you don't have to worry about that. So we have 1,120 people in the table altogether. And then how many are from R2? 155. So we put that in the numerator. And then we want to count everything from R3 that we haven't counted yet, but everything in R3 is new, right? All three of these squares, none of them came from that total 155, so we add on all 208 people from that row, and then we can go ahead and go to a decimal. And again, always parentheses when you're doing addition or subtraction. And I almost forgot to close it. That would have given me a mistake. All right, and then 0.3241. This time I stick with the 1 because it's followed by a 0. All right, so the OR is a little trickier when the things overlap. You have to be careful not to double count that overlap. But if the things are mutually exclusive or disjoint separate events, then you can just add the total for each one. All right, let's look at the final question. The person does not favor more strict gun laws, and they are not from the East. So there's got a lot of stuff going on in this. So let's translate it to notation first. The person is not, they do not favor more strict gun laws. And more strict gun laws is A1. So we want people that are not A1, and, so I'll write that in there, they are not from the East. So not from, let's see, the East is region 1. All right, so we want people that are not A1 and not R1. So this is tricky. We got to think about two nots and an and all at once. So what I want to do is try and make this visual. So let's bring in a color we haven't used yet. I'll mark this one as purple. And what I want to do is circle everything that is not A1. All right, so here's A1. So not A1 would be all of this stuff. So the A2 and the A3 columns make up not A1. Then the other part was not R1. So I want to circle all the rows that are not R1. So not R1, so it's R2, R3, or R4. So I'm going to circle these three rows right here. And now this is getting a little bit messy, but if you, let me go ahead and actually make that nice and dark. Since this is our last one, we don't have to worry about this getting in the way of answering our next question. So there's the not A1, and then let's do the same sort of thing for the not R1, make that nice and dark so it's a little easier to see and it stands out from those other colors and circles that we did already. Okay, so now there's not A1 and not R1 marked on our graph, and then let's look at the final piece. We want and means overlap. So how many things are in the overlap of the kind of horizontal and vertical purple circling that I did? And it looks like 1, 2, 3, 4, 5, 6 different squares are in the overlap of this circling and that circling. And since and means overlap, I want those 6. So I don't think I can show you all the top and the bottom at once on the camera. So let's do this. We'll transfer those numbers on the calculator. The ones that are in the overlap are 78 plus 21 plus 101 plus 28 plus 132 plus 47. Those are the people that are in those 6 cells. And so what we want to do now is say, okay, we're working out of the whole table for this question. So there's 1,120 people in the table. And then how many people were in the overlap? So we press enter. There was 407. So that was the total of the purple overlap. And then we can go ahead and put that in the calculator as a division. 407 divided by 1120 round that to 4 decimal places, and we get 0.3634, rounding that 3 up because of the 9 that follows it. All right, that wraps up this section.